Hello guys, today we're gonna be reviewing a paper, Xception, Deep Learning with Depthwise Separable Convolution. Why do I want to review this paper? It was because I'm a speech researcher. I use the neural network module, which is called a conformer. After read the paper, I read the reference in this paper to understand this type of macro network, showing the figure 1. And in that network, they also talk about the pointwise convolution and the depthwise convolution. In order to understand this, I digged further. So I found that this paper, Xception, which is a computer vision paper. I'm trying to do my best to view the paper from a speech researcher perspective and see if I can explain it well. Okay. This paper was more like a classical paper published back in 2017 by Google. The most contribution it has is to, how to say that? I think it's shown here. Versus the previous version or the baseline, which is Inception version 3, Inception v3. The proposed Xception can achieve better performance by better or more efficiently use the model parameters to get better performance while retaining the same amount or roughly the same amount of parameters. But you may ask, what's the difference between these networks and how does that work? So before we look into that issue, I would recommend we have some computer vision fundamentals first. So I made this. First of all, let's say it's bigger. This is still recording. Okay. So first of all, what do people mean when they mention one-by-one convolution? Okay. As we all know, suppose you have a convolution layer which output an tensor. Okay. The tensor has a size of n by f by h by w, and the n is the batch size. Usually you don't have to pay attention to the batch size because it's always there, and it won't change most of the time. And f means the number of a convolutional filter. But if this is a raw input image, the f can also be the number of channels, right? For example, my understanding of that is the number of channel could be, for example, RGB. I think sometimes there's a depth, right? Depth. Most time it's 3 channels. But after passing through the first convolutional layer, the original channel is gone. So you have the number of convolutional filters in this position. Okay. But H and W are easy to understand. The width and the length, or the height and the width of an image. So say the image is 64 by 32. So H is 63 and W is 32. If it is a raw image, that means that the resolution of the image, right? But if this is after the first convolution layer, this is just the spatial dimensions, okay? And suppose this is fed into the one-by-one convolution means actually they trying to mean point-wise convolution. It's a term. So initially I met this term. It took me time to understand this, but it's a terminology. You just have to remember it. It means the input is fed into a convolutional layer with F1 one-by-one filter. Okay, and with a stride size of 1. Then the output is a one-by-one convolution layer, which had the output of this convolution layer is indeed will have a shape of n by f1 by h and w. So you can see that only the f part is changed. And suppose you wanted to reduce the sensor size, you can use a f1, which is smaller than f, right? Or you want to increase the size of the tensor. So the f could be bigger than, f1 could be bigger than f, okay? So you want to have a visualization of this. I do not want to doodle this because I think this is a 3D dimensional thing. It's hard to doodle this. So I can show you this, especially this part. You can see this point-wise convolution, okay? You can see before I pass that through this one-by-one convolutional filter, I have h by w, or the f is what? F is 5, right? Where's my all this? So before that, my f equals to 5. Okay, but you see, my f1 in this scenario goes to 3. So in the end, I would have a f1 by h by w, okay? So you may ask, how does this work? But this is the standard procedure of doing convolution between a tensor and tensors. It's standard things. You can learn that by yourself. Okay, that's the first one-by-one convolution. It's actually point-wise, right? You're just focusing on or working on the channel size or the number of convolutional filters. Sometimes you can see that what do they mean by, sometimes they say 3x3 convolutional filter or 1x3 convolutional filter. Most times they meant depthwise, but you say, what if the number of output filter changes? Then the written format could be something else. So for example, they would say the number of filters. They would write the notation is like this: number of filters and n by n. It's different than this, okay? And then this one, the f does change, but if they are just saying the n by n, the f or the channel size or the number of the filters wouldn't change. They only worked on one channel or one spatial data, okay? We can see that, and again, it doesn't change. F is the number of filters, and the h and w are spatial dimensions. But in this one, after you run the convolutional filter, pass through the filter, the output size, especially the h and w, could change if the stride size does not equal to 1. You can see. I know there's a very sophisticated sophisticated equation to calculate the output size of H and W, but roughly they equals to H over S of H, and the W prime roughly equals to W over SW. So you can see that most time the strike size, you could set that as a something greater than 1, and then you would have a smaller, I think they call it active, computer vision call this activations. Okay, before you pass that through the pooling layer. Okay, they call it activations, or call it what? Patches or shaped tensors? Anyways, you can regard it as activations, okay? And indeed, this is also has another terminology. It's called a depthwise convolution. And here, let me give you an example of the depthwise separable convolution. Okay. First of all, you have a tensor of f by h by w, and for each f, for each channel, you run a depthwise convolution. Okay, like we explained before above. Okay, and then after this, you concatenate. Right, it's concatenation, or in non-CV words, is by stacking the filter output together, right? And you come up with a new tensor. Okay, and this tensor, then you apply the pointwise convolution. Then eventually you will get a tensor like this. So people may ask, why do you want to do this? Because this reduces the computational cost. But originally, most of the non-separable convolution, or a traditional or vanilla CNN layer or convolutional layer, they do this. Each convolutional filter has 3 parameters other than 2 parameters here, or just a 1x1 convolution filter here. Most of the time they have 3 parameters. Most of the time they have 3 parameters, and by doing this, you could still go from this original tensor to the exact shape of this one, but the computational cost is higher. I do not have the exact numbers, but you can do the homework by yourself, and you will see that by doing this depthwise separable convolution, the computational cost is smaller. And talking about the efficacy, the eventual classification error, there do not make much difference. Okay, so this one improves the inference speed and training speed. Okay. I can talk about this later, but let me go back to the Xception paper. Okay. So I can start from beginning. First of all, introduction. This is a paper 5 years ago. You are probably familiar with lots of the names, but they are kind of obsolete right now. Probably know the Lynette. I don't know Lynette, but I know AlexNet. Long time ago, computer vision people are using AlexNet every day, and the VGG architecture. I think speech guys nowadays. I think even 4 years ago, people are still using VGG networks, but now nobody use that one. Everybody use the transformer module. Okay. Of course, nobody use an Inceptor or Xceptor in their encoder or decoder. Everybody use a transformer, but nowadays people do use conformer in speech recognition, and the conformer does have the network structure which is similar or borrowed from the Inception architecture or Xception architecture. Okay, and the Inception network evolves from V1 to V2 to V3. I think today I will skip reading the original Inception 123 paper, just to give you a quick idea about what does the Inception module look like. Okay. First of all, you have input. The input can be raw image or what do you say that? The layers output from the previous layer. Okay, and you see that they have the 1-by-1 convolution. Okay, that's the pointwise convolution, right? And this is also pointwise convolution, and this is the depthwise convolution, right? And this is depth, and these two average pooling. So this also reduce the size of the data. Okay, this is reduce the size of data, and this is this one, right? So you may ask why people are doing this 3-by-3 convolution again. You know, they stack the two things together. You could read the original Inception paper, but the point of doing this is that I should read the Inception paper later on, but today I'm not going to do it. I just give you a rough idea, a quick idea of why people do this. Well, suppose you do originally you do a 5-by-5 convolution, okay? And then you imagine that when you swipe the convolution filter on the image sample, then to get one output, filter output, the computation is 5-by-5, right? Computation cost is 5-by-5. But suppose you can decompose the 5-by-5 convolutional operation into two smaller operations. Say you first do a 3-by-3. Okay. After you have the activations, then you do another 3-by-3. Something like this, okay? I'm not sure I'm doing a good job of this. This is 3-by-3 and this is 3-by-3. So you can see that your computational cost is 3-by-3 times 2. And this is smaller than the original 25, right? This is 25. This is like 12. Okay. Much smaller computational cost. And the Inceptor inventor researcher, they also found out that by doing this, separate the original larger convolution filter into two smaller convolution filter of 2 layers, indeed wouldn't suffer too much from the classification accuracy. So this is a good thing, right? You simplify the model size, but you retain your accuracy or your algorithm's performance. Okay. And then what this never happens. The author, this is done by the Xception authors. They say this one seems too sophisticated. Can I just simplify this by doing this? So you can see this means with one input, I can have 3 different paths, and each path have their own point-wise convolution and the depth-wise convolutions. And this one, they say, okay, seems simplified than the original one. And then later on, they say, how can they further simplify this, or say what type of a network this network is equivalent to? So after they ask that question, they say, okay, it's smaller. They say this network is indeed equivalent to this network. Figure 2 and figure 3 are indeed equivalent. So they say, because you can see that the pointwise operation on the input, this output are always the same. If you look at this output and this output and this output, they are the same. Let's call this X, and this is always Y, because this is a pointwise operation. But they can merge the 1.1 1-by-1 convolution to be just a 1. They save the computation. They don't have to do this 3 times, right? You just do 1 time, and then later on they find, okay, if you're doing this on this and this and this is also equivalent by separating the output channels from the 1-by-1 convolutional filters to 3 segments. They call these segments, I think. So computer people, if you found my explanation has issue, just feel free to comment below, okay? This is my understanding, okay? They have 3 segments, and for each segment, they run the 3x3 convolution. And you can see this further reduce the computation. They don't have to do the 3x3 convolution on the whole data. But I think this is my personal opinion, okay? This 3x3 convolution part is not exactly like this one, right? Probably the same. But I don't have time to look into the details. Let's assume that they are equivalent. And then going from the figure 3, they come up to do a further version, which they call the extreme version. And they come up, they eventually they got their Xception. And the X means extreme, okay? That's their work. And you see that the bottom part is still the same, but you can see that they increase the amount of spatial filters. You see, they have more segments. See. I do not know the details how the output of the 1-by-1 convolution filter is being segmented or generated. It seems that this one has more segments than the figure 3. That's all I observed, okay? And you can see that for this and this, definitely, I think the extreme exception or Xception has a different neural network architecture than this one. Talking about if you talk about the computational cost, I cannot tell which one is less or more. But I do have seen the results section. They say that if you look at this, they found that the Xception indeed is a slightly slower than Inception v3 in terms of the computational speed. Over here, you can see the bigger the number here is, the faster the computational cost is, the faster the computation is. Okay, let's go back to the network. And then you can see that they mentioned this, okay? Depthwise convolution and the pointwise convolution. We just covered that. Okay. One thing you may ask, why you want to do this one by one convolution, okay? What's the point of doing this? Can I just directly work on the input by doing this 3x3 spatial convolutional filter? The answer is no, because they want to use here residual connections. For those of you who have not read Dr. He's classical paper published in 2015, I think it's called Deep Residual Networks. You should read it. And that the point of doing this residual network is that suppose your input size is 128 times H times W. Here I omit the batch size, okay? I just omit it. This is the input, right? Remember the Dr. He work, and they will say, okay, let me go downward, okay? I assume the network is going downward. You want to pass this through a feed-forward network, right? Feed-forward network. Whatever DNN is, you can say DNN. At the same time, you have a direct connection to here, maybe the plus sign, right? You got the output. And let's say the output is still 128 times H and W. But the thing is, inside of this feed-forward network, you want to do something this. You want to have something, you want to generate something like a bottleneck output. Why? Bottleneck. So say in the middle, at a certain stage, the output could be 64 by H and W, or A prime at W prime. This could be changing, okay? This doesn't matter, but the size of the filter would change, or the size of the channel would change. So you can see this is smaller than this and this, and this is a bottleneck. The reason they want to do the bottleneck, they wanted the network to compress the information to see if they can learn some high-level information from the raw signal. They wanted the network to extract some useful information from the large amounts of input data, right? So they want this to be bottlenecked. In order to reduce the size of the channel, we can remember, if you remember, we just mentioned that one by one convolution. This is the way to adjust or change the size of the convolution, right? So here, usually people just apply first apply a pointwise I think I'm not doing well by writing here. Let me draw here. So they first would apply a pointwise network, okay? P means pointwise. And they get something 64 by H and W. And then they apply certain type of convolutional filter, another CNN layer, or several CNN layers. That's fine. Whatever layers you want to do, okay? And before the output, because they add these two things together, the dimension has to match, right? You have to raise the dimension of this. So you would have another pointwise layer. But you can imagine this pointwise layer is different than the first pointwise layer, which reduces the size of the channel. But this one increased the size of the channel, going from 64 to 128. Right? You see, first go down, then go up. So this is also pointwise. And I can tell you in the middle part, this is usually I say, and this is too general. Usually they use a depthwise. And my writing is totally failed. Okay, but you can see this is depthwise network. Remember that we talk about the spatial filter. It only works on one channel, each channel separately. Remember that? Let me show you. But let's see this. You can see in Xception here, you first do pointwise convolution, then you do depthwise convolution over each separate channels. They're independent of each other. Okay. I think this one they forgot to draw another one. Okay, another pointwise convolution, but it's okay. Let's go back to our paper. So now I think it's ready for us to take a look at the exact architecture of Xception. Okay, it's here. I would like you to take a look at this first. It's in Figure 5. To see if you can understand it by yourself. Okay, I guess you have paused the video and see this by yourself. Now I can start. The exact architecture goes from entry flow to middle flow, then to exit flow. So it flows like this. Got this? Okay. So suppose you have a raw image. I think this time I used to put the channel at the first part, okay, but now they put the channel at the last part. So this is H and W. HW and do I use C or F? I use F. I will stay with F, okay. But lots of people computer vision, I think they like to use the C. But I since I use the F, I will stick with F, okay. The first pass this through a standard convolutional filter, okay, with a strike size of 2 by 2. So you can imagine this one's output is roughly under, I think it's 150 times 150 times 32. Okay, 32 is the channel size or F size. Okay. The reason it has to be 150 is because 299 is divided by 2. Okay, and then you do this. So strike size is 1 by 1, doesn't change. This is what? This is 64. You can see the channel size increased. But you can see that you may say, wait, you're wrong here. It's not 150. But yeah, you're right. It might not be 150. It might be 147 or 49, something like this. But I'll just give you the rough idea of the size of the tensor, okay? And you say, okay, you missed the batch size. Yeah, of course I missed the batch size, but they also the batch size does not change during the flowing, okay? Let's forget about the batch size for now. And then this is, you can see that for here, this is the ResNet architecture, right? The input and the side loop and the summation over here. Like I mentioned that this is they talk about the separable convolution. It's remember that you first do the pointwise convolution, then do depthwise convolution, right? And this after this, what's the size of this? Yeah, still 150 times 150 times 128. So increased. This one is actually increased. Okay. Yeah, I think it's increased. And also this one doesn't change, right? It passes the Residual. So anything that after you pass the convolution filter, it usually follows the Residual or preceded by a Residual. Rectify the linear unit. Okay. And then you do this and when you do the maximum pooling with a stride size of a 2x2, here you can see that because this one also do a stride one, the convolutional filter with a stride size of 2x2, so you can see that the filter size would change. Filter size would change from 64 to 128, right? When you do size 2x2, so this size could be 75, something like 75 by 75. Yeah. So this is output, the size of this. And you get this. Clear? Okay. Okay, after you do this, then the same thing happened here. I would just skip everything here. I think this is 256. And this is more like a 37. 37 by this, right? All the same thing here. And then when you go here, you can see that it further reduced the H and W to 19 times 90. And because the size of the filter increased it to 728. And you can see that after you go flow from the raw to high level, you can see the activation size are getting smaller and smaller. What is it, activation size or the, how to say that, or image patch size? I'm not computer vision people, I don't know this. But the channel size is getting bigger and bigger, and you will see why they're getting this bigger, okay? And in the middle flow, this is easy to understand. In this one, the size of the feature map do not change, but they just repeat the Residual architecture by 8 times, okay? This is easy to understand, right? They do not change. After doing this, they're gonna be passing into the exit flow. Okay, exit flow is to generate something called a softmax or the posterior vector, something like this. Okay, then you can see over here the size would become, I would say it become 9 by 9 because you can see the stride size is 2 by 2. And then you can see that the filter size increased to 142, 1022. And then after this, this one size got increased to under 1562, 36. Then after this, further, you can see it try to improve the channel size bigger and bigger, right? And you can see this is like a, if you call that, this can be called bottleneck. I hope you understand. I explained the concept of bottleneck. They want force the neural network to reduce the size of the input at a certain stage, so the network can learn some concise information from the raw data, my understanding. And then after the bottleneck, they would increase the tensor size. And this is a global average pooling, okay? And then I think after this, they're gonna be one by one by this, okay? This is just by pooling. And this can be reduced to just a one-dimensional filter, okay? Just become instead of being a vector of the tensor, this becomes a vector. It's no longer tensor. It's one-dimensional thing, okay? It's not one-dimensional. Yeah, this is n-dimensional vector, okay, or 1D tensor. Okay, after this, they pass a fully connected layer, and you can see computer vision always using the FC or whatever. And this is gonna be that's gonna be easy. Then you pass through a logistic regression. Then you come with a, or sometimes they call it softmax layer, okay? And then eventually they're gonna be getting a, correct me if I'm wrong, I think eventually this is gonna be the output size would be a size of the number of classes, right? The size is the number of classes on the x-axis, and the y is the posterior probability. And you can see the distribution, no, sorry, the probability of each classes, right? Suppose this class gets highest probability. It means this one class is most likely class. And you can use this for CE loss calculation, or during inference you can take the max probability as the predicted class. Okay. So after we explain the architecture of the Xception network, let's take a look at the result. The result is very good. I can see that in Inception v3 and the Xception, this significantly improved the accuracy, either top 1 or top 5 on ImageNet. Okay, ImageNet. And this is the Google internal data set. It's called GFT, and you can see that these two are comparable, way better. Man, this is way better, about 5%. This is also slightly worse, but it's still 3%. Yeah. And you can see that this is a training profile. You can see, okay, this means the validation accuracy. Yeah, I think it's important. This is on the ImageNet, and this is on Google's own data set. The conclusion is similar, okay? And this is the training profile. Oh, this is without FC layer, okay? This is with FC layer. It seems that with FC layer is slightly better. And now everybody use FC layer, right? Fully connected layers. Yeah, I guess it comes from there. Efficient of the residual connection. Okay, nobody have to any doubt of the efficiency of the ResNet. Oh, I don't want to see this. Works well. Image net validation accuracy. Oh, it compares the activation. Okay. They say training profile with intermediate ReLU indeed is the worst. But if you have intermediate ELU is another activation method. But if you do not use intermediate activation, you get the best result. And they're saying that this is a conclusion, show that the absence of any nonlinearity leads to both faster convergence and better final performance. Okay, this is a very remarkable observation. I agree. So what they actually means that the depthwise separable convolution should potentially include nonlinearity between the depthwise and the pointwise operation. Oh, that's the original conclusion. But in their result, they are saying that they shouldn't have this intermediate activation. Okay. I think I'm got a little bit confused, but I think in figure 10, showing that the absence of any nonlinearity leads to both faster convergence and better final performance. But if anybody can tell me, they do use a ReLU here, right? Is it called intermediate activation or not? It seems that without ReLU is better. But I guess it's trivial since I'm not computer vision people. I'm not gonna be very much interested in that one. Okay, we have done the review of the exception, but at the last, let's go back to the conformal paper and see the usage of the pointwise convolution and the depthwise convolution in the convolution module. Let's see the figure 2. I think in the previous video, I had a question or I had a difficulty in understanding these 3 parts, because if you see the separable convolution paper, they either these 2 come up together or these 2 come up together. But not today. I understand because this is the reason why they're using the pointwise, depthwise, and pointwise, other than just using pointwise and depthwise alone. Pause the video if you can find the answer. Okay, the answer is this is a ResNet architecture. So in the ResNet architecture, you can see that suppose the number of filters here is 128, and then after pointwise, the number of filters gets down to 64, and the depthwise does not change the size of the number of the filters or the channel size. It's still 64. If you do not add this module which increase the size of the channel back to 128, over here you will have a channel size mismatch, and you won't be able to sum the original input and the network output together. Is that clear? So if you don't have this, then we'll have to add a 64 dimension and a 128 dimension together. It won't be working. Okay, so you have to have this one. All right, I think I'm gonna be stop here. And today, to have a conclusion, because we wanna understand the pointwise and the depthwise convolution in the macro net in the convolutional module, and this is why we're digging deeper and check the separable convolutions, especially depthwise separable convolution, and we go to the original paper which introduced this. It's called Xception, deep learning with depthwise separable convolutions, and we even go over the original Inception v3 architecture. Then we move on to the Xception architecture or the module, and then we go over the full architecture of the Xception, or one module by one module. And then we eventually compare the Xception versus the Inception v3 to see how well it works. And you can see that it's an improvement to better organize the neural network parameters compared to the original Inception v3. Very good research work. I'm gonna stop here. Thanks for watching. See you next week.